It is third class of chapter 4 of the course of basic geometry is show the equivalence of area of the triangle and parallelogram constructed between two parallel lines and definition, construction and calculation of the golden ratio and the golden rectangle. In this first slide of this third class of chapter 4 of this course of basic geometry, it's present figure 4.19, which shows a trapezoid quadrilateral that is composed of two lateral sides AC and BD not equal and two parallel bases AB and CD. The area of a quadrilateral trapezoid is equal to the average dimension of the two parallel bases multiplied by the height. That is, the sum of the AB and CD dimensions of the bases divided by 2 and multiplied by the dimension of the height h. In the figure 4.19, the line segment M is drawn at a distance equidistant from segments AB and CD. At the intersection of this line M with the sides of the trapezoid AC and BD are marked the points M and N. The MEC and MAG triangles are equal because they have a leg with dimension equal to the height dimension divided by 2, and the segments of the lines AM and MC that are the hypotenuse of the same triangles are also equal because the line M crosses with the line AC in its half point. The EMC and AMG angles are opposite and equals. Therefore, the EMC and AMG triangles have the same areas. One triangle is external to the quadrilateral trapezoid, and the other is internal to the quadrilateral trapezoid. In this slide, a demonstration for the two triangles DFN and HNB is done in a similar way of that presented in the previous slide for triangles EMC and AMG. Therefore, we can say that the area of the trapezoid quadrilateral ABDC is equal to the sum of the areas of the two quadrilaterals trapezium CMND and AMNB. The area of the quadrilateral AMNB is equal to the area of the rectangle GMNH, which is equal to A equal M multiplied by H divided by 2, with the addition of the area of the triangles AMG, H and B. The area of the quadrilateral CMND is equal to the area of the rectangle EMNF, which is equal to the dimension of the straight line segment M multiplied by the dimension of the line segment H divided by 2 minus the areas of the triangles EMC and DFN. The triangle AMG, that is equal to the triangle ECM, and the triangle HBN, that is equal to the triangle DFN, are added to the rectangle GMNH, and they are subtracted to the rectangle EMNF. The addition and subtraction of the area of the triangles results in a zero value to the areas corresponding to the triangles, and the total area of the trapezium ABDC is equal to the dimension of the straight line segment M multiplied by the dimension of the straight line segment H. Then, the formula of the total area of the trapezoid ABCD is equal to the dimension of the straight line segment M multiplied by the dimension of the straight line segment H. But the straight line segment M has a dimension equal to the sum of the dimension of the straight line segments EB added to the straight line segment CD divided by 2. Thus, finally, the ABCD trapezoid area is equal to the sum of the dimension of the straight line segment AB B with dimension of the straight line segment CD divided by 2 multiplied by the dimension of the line segment H. This slide presents the theorem relative to the equivalence of the areas of the triangle and parallelogram constructed between parallel lines using the same base. The proof uses figure 4.20, which two parallel lines AB and DE are drawn with a distance h between them. A straight line segment AB is marked on the lower parallel line. Points A and B are the two vertices of the base of the triangles ABC and ABE, and the also of the parallelogram ABCD. The areas of the triangles are calculated by multiplying the dimension of the straight line segment AB by the straight line segment AG divided by 2. The parallelogram is formed by two identical triangles, ABC and ACD, since the straight line segments BC and AD are parallel, and they are between two parallel, making them equals. In this slide, you continue the demonstration of the theorem related to the equivalence of the areas of the triangle and parallelogram constructed between parallel lines using the same base. Continuing the demonstration, the straight line segment CD is equal to the straight line segment of the base AB, because both are between parallel lines and they are also in two parallel lines. Therefore, the triangles ABC and ACD have two equal sides and have the same areas. Then, as the parallelogram is composed of the addition of the two equal triangles, the area of the parallelogram is twice the areas of the triangles. Thus, you can state the theorem as a triangle and a parallelogram constructed between two parallel lines and having the same base on one of the parallel lines. The parallelogram will have twice the area of the triangle. This slide shows the definition and properties of the golden segment and the golden rectangle. If you divide the line segment AB into two segments, AF and FB, and the rate F is equal to the dimension of the straight line segment AB divided by the dimension of the straight line segment AF, and also equal to the ratio of the dimension of the segment of straight line AF divided by the segment of straight line FB, and also has a value equal to 1.618034. This number is called the golden ratio or golden number. The inverse of this number is given by dividing the unity by the number 1.618034, resulting in the number 0.618. If you construct a rectangle with one side with value 1 and the other side with the value of 0.618, this is called the golden rectangle. The figure 4.21 shows the construction of a golden rectangle and also the demonstration of the generation of the golden ratio and of the golden number. This slide shows the construction of the golden rectangle in detail. Initially, a straight line segment is drawn and defined by points A and B. At the point B, one perpendicular to the straight line segment AB is raised equal to the half of the dimension of the segment of the straight line AB, determining the point E. Next, it is drawn the straight line segment that join the already established points A and E, called the straight line segment R. We center at the point E, and with a radius equal to the dimension of the straight line AB divided by 2, we draw an arc beginning at the point B and ending at the point G. We center at the point A and radius AG. The arc is drawn starting at the point G and ending at the point F. Therefore, we determine the point F that divides the line segment AB into the golden ratio. This slide shows the figure showing the segment AB that is considered with a unity value in two segments of a straight line AF and FB. Figure 4.21 shows that the value of the golden ratio is equal to the straight line segment R minus the value of the straight line segment A, which has the same value as the straight line segment AB divided by 2. Based on the relation of the right triangle ABE, the relation between the line segment R, which is the hypotenuse, and the straight line segment is obtained, which is one of the other two legs. This result says that the segment of a line R has a value equal to the segment of straight line A multiplied by the square root of the relation 5 divided by 4. Thus, based on the definition of a golden ratio and substituting the calculated R value, the result for the golden ratio is 0.618 multiplied by the dimension of the straight line segment A, which is set to have the value of the unit. Thus, the golden ratio has a value of 0.618. Realizing the inversion of the value of the golden ratio, the unit value 1 is divided by 0.618, which results in the factor f, which has a value of 1.618034, called the factor of Phidias, or f. Thus, the division of the dimension of the straight line segment AB by the dimension of the straight line segment AF results in the factor f. Also, the division of the dimension of the straight line segment AF divided by the dimension of the straight line segment FB also results in the factor f. Continuing with the construction process, a perpendicular is drawn at the point A. With center at the point A and radius AG, the arc JF is extended to point D, which is at the perpendicular raised at the point A. Thus, the rectangle ABCD is constructed. This rectangle is called the golden rectangle. This rectangle has the AD side with a value of 0.618 multiplied by the value AB, which is the straight line segment of the base AB that is assumed to have the value of the unit. Thus, the construction of the golden rectangle and also the subdivision of the segment